And the occasion for this, oh, and I also wanted to mention that during my plenary talk, my session chair was Professor Dr. Paul Leiser, who is an alumni of this department, also a former student. So it's really nice to be introduced by my students in my group in both talks. So what I wanted to do is the reason I got invited to give this plenary was the recognition of a talk I gave 30 years ago, which was actually literally half a lifetime ago. So I wanted to talk about that paper and kind of talk about how it came about, because there's kind of a story about that. And then to kind of show you an illustration here of what sometimes can happen. And just looking at the year after this work and how things dramatically changed. And then I'd like to look at what we call commercial VCSELs, because you may be surprised at just how ubiquitous they are. And then since this is an hour talk versus 30 minutes, I might say a few words about what may be after this. But the perspective I want to take on this is that a couple of weeks ago, a month ago, during the Holonyak workshop, we were fortunate to be visited by Umesh Mishra, who is from UC Santa Barbara. And Umesh he was here to to speak about the gospel of gallium nitride high-power devices. But the point that he made in his presentation was that, as researchers, what you really want to do, particularly in semiconductors, success can be defined by when your technology becomes adopted by everybody, becomes a commodity. And I think that's the perspective I want to take today. So I mentioned this was 30 years ago, and I was about half of my age. Back in '94, cell phones were literally the size of a brick. They didn't have cameras. We used real cameras to take pictures. So I've managed to find some old pictures. This is a very young Kent and Lori, my wife, looking into the crater at that national park there in Maui. And this is a very young Kent standing next to one of those big giant trees. And again, I found postcards. I didn't find very many pictures. We were out, this was literally 30 years ago, and we were out there a few days before the conference, because leading up to this conference, I was working like very, very hard, literally living in my lab at Sandia National Labs. So I kind of had to pay back my wife a little bit. And the reason why was because I was really working hard to get this paper out, which is what I presented in the post-deadline session. The International Laser Conference, it's been a tradition that on the last day we have a post-deadline. And this is supposed to be where you bring in your hottest results. And so again, we were literally printing this out as we were on the way to the airport. So this was basically a paper that we presented. And in this paper, we basically showed this work where you looked at the oxidation rate relative to aluminum arsenide, found that you could vary the rate very carefully with selective control of the composition. And so you could look at this structure where you could put in an oxide aperture and buried inside of a monolithic TBR, which was then and now the structure for VCSELs. And it works really, really well. It's surprisingly well. At this time, I didn't have the sort of masks and things that we have today, so I was actually limited to some really big structures, so I can only make fairly big things. This is something like 10 by 10. There was a couple cases where I made some really small structures, but these were, they showed some extraordinary characteristics, including a threshold voltage that is yet to be exceeded. That in terms of the voltage above the photon energy, these devices were amazing. And there's a reason why, and I'll tell you a little bit about that story. Now during this conference, we didn't have PowerPoint. We had overhead projectors. And I realized that up until a few years ago, we used to have them in our classrooms and they disappeared. So, and I thought I would bring an example of one so you see that I'm not making this up. What I did is I actually found some of my old field graphs from that talk. This is kind of amazing. I actually had to go home and find a computer that could still open up those little things. But back in those days, we had view graphs on pieces of paper. On an animation was when we would like flip something over it. Okay, so that's what, you know. But so this is some of the view graphs from that talk. I basically showed some of the work that grad student Dallas Sassy, some of the work you're doing here in this department, which you realize that if you oxidize aluminum arsenide, you're down to this new phase, which actually is much more stable than what you find at room temperature. But furthermore, I also showed this work, which has since been colorized, where basically we looked at this material where we were interleaving very high concentrations of aluminum. Basically, we're just changing by 2%, nominally 2% gallium. What we're really doing is this is calibrated to the growth machine. So this is done by MOCVD. So these are various flow rates of gallium and so forth. So you can see this oxidation dependence. And what this allows you to do is through tiny changes of composition, if you can do that, you can very much control this oxidation extent. So this was, we didn't have, this was before we got the TMs going. We had just got one of these cool thermal printers on the SEM, so I could do some work at night, which you can no longer do at Sandia in the clean room. I could look at the cross sections and I could print out these little printouts, and so we could see these oxidized layers in the stack, and then we made this our oxide. In this particular structure, we put one oxide layer, and later we were doing oxide on both sides. Today, it's pretty much just one side, because we really can't control the two oxides to make them good, but as we could back then. I don't know why. Anyway, this is, I was telling Chloe this yesterday. We had in the lab, again, I'm a young staff member working after hours, you know, kind of illegally in the clean room. And they had this microscope that you could use, and I learned later it had an Normarsky contrast. And so you can change the Normarsky contrast, and what you're looking at is looking down on one of these mesas, and there's that oxide aperture. You're looking at 2.5 microns of DVR. When I left Sandia, couldn't reproduce this until about 2 or 3 years ago. I learned that the camera was really the key part of this. But this is where you can actually see these apertures. Again, this was colorized, but the data that I showed was at the time, the technology that was being used was ion implantation. That basically renders the semiconductor non-conductive. You can confine the current, but it does nothing for the photons. And so I had made a bunch of implanted VCSELs out of this wafer, and then later I made some oxide. And so we could compare, in this case, the current densities and the threshold voltage. Again, I had to compare current densities because I had very hard to control the sizes at this point, because I had really big. I didn't really understand how to do this. But you can see that we saw a tremendous reduction in the threshold currents. And if you converted that into threshold currents, these were well below milliamp, which at the time was just unbelievable. That was the whole thing that got us excited about this. This is the threshold voltages, and I mentioned some of these points here are only less than 100 MeV above the photon energy. And that's coming about because the oxide aperture provides both index confinement and electrical confinement, which the implanted structure didn't. So, and then the other data that I showed, which is amazing, I keep showing this after 30 years, is this. If you take my 572 course, you'll see this in class. And basically what this is tracking the transverse modes of a microcavity laser, in this case an implanted device, as a function of current. And so each of these lines corresponds to a different transverse mode. So the first one here, longest, will be the fundamental mode, and we climb up as we go. So this is very much what we saw in this time frame, where you basically got the fundamental mode laid at threshold, but very soon, because of hole burning, we would see other modes sequentially turning on. Of course, they're all blue shifting, because you're heating, this is CW, so you're heating up the whole structure, and the index is increasing, and so the whole thing is basically shifting to the red. Now, conversely, if you look at the oxide VCSELs made from the same structure, they have very different modal behavior. Then at threshold a bunch of modes all just turn on at once. And this is indicative of that index confinement that is inherent from that buried oxide. The other thing is you'll see is that in these such structures, you actually see a blue shift in the wavelengths before you see the red shift. And this red shift is, of course, the thermal effect. And what this is indicating is that when, again, the oxide is confining the current, but it's doing it so efficiently that we're not heating up. And so what you're seeing is the suppression of the index due to the current injection. And then eventually we are heating things up. Let me get back on the red shift. This current suppression is the thing that we're currently now in our group trying to exploit to basically build coherent arrays. And this was a mystery back then that, solving it led to what we're continuing to work on. Okay, so where did all this work come from? So I want to tell the story behind this because there was an interesting story, and there was a lot of events that came together all at once. So the story starts with CLEO in 1994, and the Conference on Lasers and Electro-Optics, one of the major forums to talk about research. And remember, this is before the internet and really the extensive use of email. So we were literally sending mail to each other and going to conferences to hear about the latest stuff. So in 1994, the post-deadline session, which is to this day is on the Thursday of the week, it's usually a big deal. The first talk of the post-deadline session was the first demonstration of the quantum cascade laser from Federico Capasso. The second talk was supposed to be given by researchers at the University of Texas who are going to come and tell us about some very interesting VCSELs that had a really low threshold, but they didn't show up. This, to this day, is one of the only times I've ever seen someone not give a talk at a post-deadline at CLEO. About a month before that, this paper came out from the same group, and this is Diana Huffaker and Dennis Steppe, showing basically a layer of oxidized aluminum arsenide with a thin layer of gallium arsenide, and showing a current aperture, which is a very nice, nice structure, but it's not what has been used. And in fact, in the paper, it mentions the fact that these devices are not very reliable. And in fact, we understand why, because they were using aluminum arsenide. So, this work then, so I go to this conference, the whole Sandia team is at this conference, and we don't see this paper. So we go back that summer, and I had Rick Snyder, who was the MOCD grower, grow this structure looking at the various compositions and sort of devising this device structure. At the same time, a colleague of mine, Kevin Lair, who, by the way, I was a classmate with at the University of Colorado as an undergraduate, he was busy working on making transitions between the high and low index layer to reduce the series resistance. And by basically reverse engineering Poisson's equation, he came up with what's called the uniparabolic grade, which is the most efficient way to grade between two indices. I will have to say that grade is so complicated that it's not practiced today, but it was an extremely low resistance mirror. So I gave Rick Snyder, who was our grower, who he's also a crack device engineer. He's at that time working on red VCSELs, trying to understand how to grow aluminum arsenide materials, indium phosphide-based materials, and then go back to aluminum arsenide-based materials to grow the structures. So he's just a great device engineer. So Rick gets both of these designs, so he combines them. And he grows two wafers. He gives one wafer to Kevin and one wafer to me. The wafer he gave to me had 25 top period in the DBR to sort of guarantee that it lased. And then Kevin got, I think it had less 19 or 18 pair because he was trying to make high efficiency devices. So this is toward the end of August. So I'm busy making and doing all sorts of calibration. I carved up that wafer, tiny little pieces, and did all these calibration. It's a terrible shame because it was a great wafer. And made some implanted VCSELs, made sure it worked. And we finally made some oxide-confined VCSELs, which then we struggled to get together some paper, get it out to that at the International Laser Conference. And then at that time at the Sandia, we had to give the talk, and then we could give the paper. And in fact, we had to, in this case, get the patent applied for. So it wasn't until October that we could submit to electronics letters, which at the time, that was the fastest way to distribute information, because electronics letters was just up or down. There was no revision. Usually you were published within like 60 or 90 days, back when that was just not even heard of. So I got this paper out again. It was basically a repeat of our ISO-C paper. But then, so I'm busy testing some devices, and at this time I don't have my lab all set up. So I was working in Kevin's lab, and so I tested some of the devices, and basically I pegged the power, the detector, and just flat out saturated it. So I said to Kevin, you gotta get a better detector. He said, no, you didn't do the measurement right. So I said, okay, here are the devices, and he went and he tested them. A couple hours later, he came back, and he said, oh, we got 40% wall plug efficiency on these devices. Now, to put this in perspective, he's working with the wafer that he has, and he made a bunch of implanted VCSELs, and he was basically seeing and would report a 21% wall plug efficiency, which at the time of an implanted VCSEL, that was absolutely stunning, because that was like 5 times greater than anything ever done in a VCSEL, and actually was starting to rival edge emitters. All right, 20%. And so then this lab mate just threw a sample on there, and we doubled it just in a blink. So Kevin was motivated to make some oxide VCSELs with his wafer. Turned out his engineer was shared an office with me, so we got those devices made. And by Thanksgiving, and he had smaller mesas and things. So by Thanksgiving, we had a device that was showing the 50% wall plug efficiency. This was the paper that appeared, it appeared actually in January, but we got it out before 494. And this was the paper that was, this is the shot heard around the world, because 50% wall plug efficiency was absolutely not unheard of. This exceeded by a factor of 2 in the best edge emitter. And again, I was twice and 2.5 times better than the best VCSEL that was on there, and literally a week before we started looking at these. So this was absolutely stunning. Kevin wrote a report. This was a report, you can actually find this online, where we were basically in this time frame having what's known as LDRDs, Laboratory Directed Research and Development. These are funding mechanisms that still exist today to fund academic folks. But in any event, this was an LDRD. We had like 4 or 5 doing oxide stuff. And you can see Kevin's slowly plugging along on the wall plug efficiency, gets up here to the 21%. And then, overnight by making our oxide VCSELs, we were up there at 50%. So this was really something that caught on. So what happened next was what I would consider to be just an absolute avalanche, is that every group, every research group, and every company in the world suddenly were starting to working on oxide-confined VCSELs, because it was a process that was very straightforward, very easy to do, and you've got great devices. I showed, I just pulled out files out of my file. I don't think this is complete. This is just in 1 year. And you can see all the groups. Now, when I presented this last week, I got a laugh, because basically, even Larry Coldren could find something that he could embrace with the oxide-confined VCSELs. And Larry's kind of a very, if it wasn't invented here, it hasn't been invented. So it was, and it was absolutely a stunning avalanche. So, and again, we had a bunch of money internally. I worked with some really wonderful people at Sandia, chemists and physicists and material scientists, growers, and we had a bunch of internal funding. We were oxidizing every compound semiconductor that either had aluminum or antimony, the 2 reactive materials. Basically, there's lots and lots of work done, but the only thing that really stuck is this work. So this is, again, we were looking at the oxidation rates of varying the composition. the key thing that was really interesting here is these are linear oxidation rates. So when you if you go back to your 444 notes, you will realize that the oxidation of oxides is parabolic, and the only way that you get linear is because of the geometry of this structure, which is we're laterally oxidizing through layers that are confining the oxidation rate. So that gives you very linear rates with no induction period. This is one other thing that I was trying to explain to Chloe yesterday, is you can etch these structures, and if you're not doing stupid things with them, you can come back weeks, maybe even months, maybe even years later and oxidize it. Now once you've oxidized it, you can't re-oxidize it. That's a problem, but it's a very, very, like I said, forgiving process. It follows a ringness relationship, and basically what you see is that moving from aluminum arsenide to just down to 90%, you're going from less than an EV activation energy to just less than 2 EV. And so this is why you can have such tremendous control over the rates relative to the oxidation. So again, we did all kinds of studies and looked at this. Basically, right at the start, we were working with gas because that worked, frankly. And then later we figured out why, and that's because a little bit of gallium is good, because that fills up the volume that you lose from when you oxidize aluminum arsenide. Again, we figured out this process. It's important to have hydrogen. Later on, researchers figured out that if you put in oxygen, you can control this, which basically controls the oxidation rate. But it's still, to me, it's better just to do the steam because it's very straightforward. To this day, it's still just basically a timed process. But with this, you can do, what I would argue is you can do design. So this is some of the first structures here. Looking at, I know this is a terrible image because it's an image of a view graph that I have. But what you can see here is this is the oxide layer. There's 5 quantum wells here, and there's no. The key thing is there's no strain now. Then if you go ahead and control the compositions, and you can play all kinds of games. We can move, we can oxidize various layers. We can. This was meant to be to kind of affect the capacitance. We can put thin layers on the null of the field. We can put tips. This is structure where we're varying the composition in order to put a tip either on the null or the field. So we did lots of things basically. What we learned is that really that you really don't have to do much more than just try to make it as thin a layer as you can. We learned why you want to use algas. Basically this is a structure using algas, this is a structure using aluminum arsenide, and the key difference here is that oxide gives you a lot of strain. It's not obvious in this image, but this is the image that is very obvious in. That this is a structure looking down at the oxidized mesas using algas. If they're using aluminum arsenide, they explode. And the joke I made that just went right over everybody's head was that, well, these explosions were too small to be noticed at Sandia. Okay. What's that?
You're referring to the nuclear stockpile?
Yeah, well, let's just say that we were, the people there were sensitive to vibrations everywhere in the world. Anyway, we also looked at visible VCSELs, and actually at the time, that's what I was hired to do, was to work on the visible VCSELs. So the first thing I did is first thing that Rick did was he put these oxide apertures in there, and overnight, again, we saw big changes. Getting threshold currents on in a visible VCSEL below the threshold was just unprecedented, and this led to a bunch of programs, which led to the formation of what today is called, what then was called Honeywell VCSELs, which then went down to Texas and became AOC, which then became Finisar, which then became 2.6, which today is coherent. So this work actually had a big impact in the ecosystem, if you will, of VCSELs. Again, by the summer of '95, we were doing some of the first lifetime testing, finding these things were rock steady. So this was some of the internal propaganda that came out. There's a young Ken sitting here at the probe station. But I want to point out, this is Kevin Lear and Rick Snyder, the two gentlemen that I work with, that again, if it wasn't for Kevin's designs at the time, and it wasn't for Rick being able to bring them together, this probably wouldn't have all happened like it did. But what I want to show this for is that right there is the oxidation furnace. And what I did is back in the corner of the lab, there was an old LPE, a liquid phase epitaxy system. You guys don't even know what it is. I didn't know what it was. They told me that after I tore it apart. But we basically converted it and made it into a quick and dirty oxidation system, which is all this stuff was really done. So you can say, well, what do you got to do if you're going to try to manufacture oxide-confined VCSELs? And this is a slide that I actually showed has been since colorized at that first post-deadline talk. And basically what you need to have is a furnace and control your temperature and introduce steam. What's interesting is at the time at Sandia, we had to worry about the exhaust because Sandia was extremely conscientious about environmental safety for very obvious reasons. And so there is this thought that perhaps we were having arsenic being dissolved out in fluid. And so we tested it, and it turned out that the amount of arsenic in this output was less than what we found in the drinking water. That Albuquerque has a naturally high amount of arsenic. I should probably tell you that. So this is part of the concern. This is what I thought at the time, and this is what we continue to use today. I put this picture up, and the alumni who my group at the conference all kind of groaned because I got a question, how important is it to be clean? And everybody was laughing about this lab. This is probably the most unclean lab in the entire MNTL. Anyway, this is what we use. Now the question is what do they use in industry? So back in August, I started to tap into the folks that I know of in the industry and started to ask them, hey, can you send me a picture of your oxidation furnace? Of course, they said no. And in fact, they couldn't even tell me they wouldn't tell me what kind of furnace they used. They would say, well, I'll send you a picture. And they send me a picture. Then I say, well, I'm going to send you a paper that's important. Well, they send that. And then all these papers and pictures are all the same thing. They're all using the Koyo, this baby. This is a big, giant vertical furnace that can run 56-inch wafers at a crack. It's a so-called convection furnace in the sense that these wafers are all sitting in an ambient that is very, very carefully controlled. And the key, as I'll show you, the temperature control is what is key. It turned out that there's actually single wafer versions of this if we want to get something in MNTL. This was something that our visitors from Cardiff pointed out. We have single wafer versions of oxidation systems now. So I think 2 weeks ago, or maybe 3 weeks ago, our last speaker was Jack Baker from Cardiff, and he was part of the compound semiconductor cluster in Wales, and that's a bunch of labs and things that are basically anchored centered around IQE. IQE is one of the biggest sellers of epitaxy in the world. And so then Jack showed this picture. What is it that's being oxidized today? And so this is a picture of a 4-inch VCSEL wafer for basically datacom, or they're looking at atomic sensors. By the way, I could have brought in and then this is an example of a 6-inch wafer, a LiDAR wafer. I could have brought in an example of a 5-inch one. We just recently got one in the lab. It's amazing. So these are gigantic wafers. These are so big that the difference between gallium arsenide and aluminum arsenide matters, in that when they grow the stack, that there's enough, the discontinuity between the two lattice constants is enough that these wafers bow. And so when you, and this is data that Jack showed, is that if you look at the oxidation rate, and that's what this is basically looking at the oxidation extent. And basically what we're seeing here is that the rates are, the extents are greater on the edge than they are in the center. And the reason for that is that the edges are hotter than the center because the thing is bowed and it's popping up. And Jack was mentioning in 6-inch wafer had to be two or three microns at the center there. And so, of course, how you solve this is this is the same data again. What you do is you use a convection furnace, like I showed you, in those multi-stack vertical structures, and then you get much more uniform variation. I was actually stunned that IQE would do these kind of experiments because IQE is an epitaxy company, but again, because, as you'll see, oxide VCSELs are just essentially a commodity. That when you say VCSEL today, they mean, it has an oxide aperture in it. And so even epitaxial companies have to worry about the uniformity of this layer to sell to their customers. So this is an example of a datacom VCSEL. This is about 2015. This is probably a device that was made around 2012. I don't want to tell you why we are looking at these pictures, but it was a former student who we had some money to do some carving. What you can see is this is a conventional device. We can cut right through the mesa. Notice, by the way, this is a structure which the metallization goes down the trench and up the mesa wall. This is the very thing that I could never seem to ever accomplish. But anyway, you look at a cross section and you can see the oxide aperture. This turns out to be about 8.5 microns, which at the time was a big deal. And essentially, these things have been, as I'm going to show you, made by the billions. And why? They all are basically running, sub-milliamp. They basically operate at just a milliamp or so operation current. You can have single mode, and they're just, you really can't find any more efficient device if you just need a few milliwatts. So in 2014, we celebrated the 20th anniversary of the VCSEL conference at SPIE, and it was started about the year we started this oxidation work. And so I've been involved with that conference ever since. And in 2014, Jim Tatum, who at the time was the CEO of, at that time was Finisar, yes, this is Finisar, gave a review of the status of VCSELs. And so today then was in 2014, and at that time, there's something on the order of 10,000 3-inch VCSEL wafers being shipped every year, being driven, and it's mainly being driven for, at this point, datacom, and a little bit of, well, some of this is also in your laser mice. And the thing I want to point out is that in 1996, we were all doing implantation, at least in the commercial world. But by 2014, it had converted to this oxide-confined. And actually, that transition happened about the year 2000. So, and you can see that in other trends. So this was a slide that Jim showed, showing, and he was just looking at the die size. But I'm looking at the kind of VCSELs that are here. Now, you young whippersnappers don't recognize this, but this is an oxide-confined VCSEL. There's the contact, there's the VCSEL, you don't see anything. This is an implanted VCSEL, implanted VCSEL. This is an oxide-confined VCSEL because you have the holes that you need to use to introduce the oxidation, and similar in this structure. So you can see that at about 2000, we were evolving from commercial VCSELs doing implants to commercial VCSELs all being oxidized. Why did this happen? This happened because of the demand, the demand for what that time was a killer application, which was datacom, data communication. We wanted to basically send bits as fast as we can through about 100 meters of fiber, because this is the advent of data centers. And at this time, the number of interconnects that were envisioned less than 100 meters was orders of magnitude more than greater than that. Basically saying that there would be a lot of data centers in the world. So you can look at this in terms of the speed of the device. So this is a so-called 10 gigabit, 20 gigabit, or over 20 gigabit. But basically, if you overlay the speeds, that basically before 2000, we were running at around 1 gigabit. And around 2000, we had to get above 2.5 gigabit, to get to 2.5 gigabit. And I remember having conversations at our VCSEL conference, like, how the heck are we going to do this? Well, it turned out that, again, that very first wafer went back to it, made some high-speed devices, and got, you know, record modulation performance also. So it was very clear that in order, and the problem was implanted don't have index confinement. And so to get high speeds, you had to use oxide. And so this is the transition that happened and just never went back. The other part about this story is part of the success. I like to say it's a double-edged sword, and that these were incredibly reliable devices when you used aluminum gallium arsenide as your oxidation layer with 98%. So if you think that this is some data that again that Jim was showing from Finisar, and if you look at the data rate and the lifetimes that they were estimating from their testing, you can see that at the low rates, and again these are implanted pixels, that the implanted pixels did get up to where you could, you know, where the lifetimes were measured in a century or more. Right? This is over 100 years, 300 years. But clearly, the oxide pixels showed the same kind of reliability, and that's been the kind of the bane. Anytime you introduce something new in the VCSEL world, first thing they say is, "Well, how reliable is it? Can they throw it up against this kind of reliability?" And the reality is that there is no other optoelectronic technology that's as reliable as the VCSELs. So I tried to ping my contacts out the various companies. Basically, over time, when I started out in '94, there was, I don't know, 24, maybe 30, lots of startups, you know, VCSELs doing VCSELs. Over the years, it's sort of consolidated now. It's been really small. But so I mentioned this was from, I talked about in 2014 as Finisar. Later that turned into 2.6, which has recently turned into Coherent. I contacted Deepa, and he pointed me to the website, which, you know, showed me that, you know, they're like a lot of companies are looking at these double junctions, these high-speed arrays, and what's interesting is estimating that they had, you know, deployed about 200 billion pixels, basically as sensors in iPhones. So now I reached out to Ramana at Broadcom, which if you go back in time, is started out from HP Labs, and again I have a bunch of several students who work there. From the point they pointed out that yeah, this is Broadcom, Avago, Agilent, all the way back to HP. That if you look at the rollout of the modulation rate of these systems that the VCSELs are being used at, that it's following a Moore's law, like a trend, where you're basically getting a factor of basically what is it, a factor of 2 for every couple of years here, and that has been basically driven by the fact that the oxide-confined VCSELs can drive this, can support this. And so this is the example of their transceivers that they showed at OFC this past year. You know, today we don't do simple 0 and 1s, we do 4 levels. This is so-called PAM4. So this is just done as a means to go to have higher modulation rates. You know, the fundamental issue here is we can't directly modulate the laser greater than about 20 to 30 gigabit. And to go faster than that, you have to do something external, which is where the rise of silicon photonics comes in. However, there was something that again happened in the VCSEL world that just happened a few years ago that changed the entire way we think about things. Because as I said, I talked about this in terms of datacom, where you basically make a single device, or maybe you make an array of 10, but you know, they were basically single devices. We're going along here, and actually I was at Coldren, got retired in 2017. They had a little bash, and they were, you know, yelling and screaming because they thought we had about 1 billion VCSELs deployed. And then Apple did an experiment in 2017 where they put a VCSEL in the AirPods as a proximity sensor, so when you put it in your ear, it turns on. And that was so successful that they deployed the arrays for basically sensing, and so the consumer product of VCSEL array era kicked in. And at that point, you know, we were, instead of making 1s or 2s, you know, that, you know, in the, you know, this version of the phone, there's 313 pixels in here. And so, again, I gave this talk last week at Disneyland. So in some sense, this was, you know, the number of pixels just went through the roof. And this happened literally overnight. And so we're now in the era of arrays, pixel arrays. And so Eric Hegblum at Lumentum sent some slides, and essentially it's really interesting. I polled all these folks, and they all managed to independently send me back different applications. So I think the companies are kind of lining up between various applications. You know, what they're banking on is a lot of sensing and LiDAR applications. Here's a diagram or a slide he sent showing these pixel arrays where basically just the layout of the emitters, these are all incoherent, all run in parallel. This layout of the emitters coupled with some a very simple camera, I should say a very inexpensive APD with some electronics, and you can do all kinds of things in terms of time of flight and identification. One thing I wanted to point out though, and this was something that during that conference, everybody was talking about LiDAR and applications. Look at the, and what's happening here is they're trying to put a peak power, they're pulsing it, so it's peak power. But look at these peak powers that they're talking about. 5 milliwatts, 5 watts per millimeter squared to a kilowatt per millimeter squared, all right? That's some substantial power that, you know, someday we may be, when we're driving our cars, we're gonna be subject to being exposed to. I wanna just point out, and everybody was pointing out, looking at eye safety, but if you think about skin exposure, that at 850 nanometers, we're limited to a milliwatt per millimeter squared. Now this is CW, of course. But, so I'm wondering in the future is if we not only will be wearing glasses with coatings, we'll be wearing coats and we'll be wearing clothes with anti-reflective coatings because there's gonna be a lot of emission out there. Anyway, what's driving this from Lumentum is the use of multi-junctions. Instead of using one p-n junction, you make a p-n junction, you put in a tunnel junction to convert your hole to an electron, and then you put in another junction. So you're just cascading the junctions. So at the price of a higher voltage, you can recycle your carriers, but it's in a bipolar device. But in any event, this is an example of 3 stacks, and you can now get some pretty hefty peak powers. This is approaching a kilowatt. And again, yeah, I think that, and then the thing that's driving this is basically the confinement through those junctions, which is all done with oxide confinement. So Lumentum sent this slide, and again, think about this from their perspective. They're viewing VCSEL's development from the perspective of these arrays that they're building for, you know, sensors, you know, depth control, AR, and so forth. Okay, so you know, and they were very excited about, you know, reporting 200 billion pixels that they deployed. But look at that number right there. There is an estimate that given from, you know, I'm gonna say that the implanted pixels are irrelevant, but basically there's been over 1 trillion VCSELs deployed for applications. And those VCSELs all use a 98% oxide aperture in a monolithic mirror. Just to put this in perspective, what is 1 trillion? Well, okay, we compare this maybe to a penny. Okay, and actually it turns out that the U.S. Abraham Lincoln is the most sculpted human being in history, in humankind, because he's on the penny since 1909, and there's about 25 quadrillion. Again, since this is a talk here, I just wanted to make sure. Trillion is 10 to the 12th, quadrillion 10 to the 15th, so we're still 3 orders of magnitude away from, you know, the lowest doping, you know, typical doping density in a photonic device. Okay, so what's next for VCSELs? Just a few words, you know, if you're trying to do, you know, because of the simultaneous index and insulating properties confinement, no one has really found any better structure. And I've actually heard a lot of people said they tried. And it's got incredible reliability. You can get, incoherent power levels. So, if you have tens of milliwatts CW, you really can't do anything better. But what are the downsides? Well, one of the big downsides is that strong index confinement. That if you want to make a single mode device, that's a problem. Because this essentially will dominate and basically make, as you saw, when you, a threshold, you can support multiple modes because you have no modal discrimination. And so that's why when literally, in 2000 is when I joined in Illinois, and this is when I started working on photonic crystal VCSELs. And the idea behind this is that essentially, if you want to make a single mode device, if you want to go to implants, basically we got to make it 5 microns in diameter, which is always why we're trying to make those implants 5 microns in diameter, which is a real pain. On the other hand, if you want to make a single mode oxide-confined VCSEL and you work like heck to put the thin layer on and all the business, the best you can do is something on the 10-2, which means that your device to be single mode has to be 3 microns or smaller. That is just not reliable. Trust me, a lot of folks have tried to. This also turns out as you make them smaller, you can increase your modulation. But again, if you can modulate all you want, but if you're not reliable, no one will touch it. So of course, what we've been working on is to introduce a photonic crystal to intermediate that. So ion implanting gave you no index confinement. Oxide, even when you work to design it below, just gives you really strong confinement. But the implanted oxide-confined VCSEL allows us to actually design, and that's kind of what we've been doing over the years. So you can take, basically this is your multi-mode, high-efficiency VCSEL. You drill holes into it, and you can basically make this a single-mode device. And the other part that we like, because it makes it a lot easier, is you can use the same design at different wavelengths. There's a so-called easy single-mode configuration. And so this is my last slide. Now we look at these for making arrays. And again, what's interesting is in order to induce this coupling, we're trying to exploit this injection aspect. Okay, so this is my summary slide that I gave 30 years ago. It's obviously not in the same format, but this is the same word. And so I had to, of course, move the formats. But the thing I wanted to point out is that on my mask, I happen to have somewhere on it a Sandia emblem. We call this the Thunder Chicken. And just by accident, there was an aperture underneath it, and it just struck me as looking like a heart. So I remember saying, I thought that maybe VCSELs would be, the oxidation would be the heart of VCSELs. And I think that's come true. That today, when you say VCSEL, you mean monolithic, selectively-oxidized VCSEL. So I want to thank, I had a lot of people who gave me input. I had a few slides. Mainly they talked to me, and so I just kind of referred some of this stuff. And I want to thank you for your attention.
Thank you very much for giving a fantastic talk today. I think we can open up the floor for questions before we break for lunch. Is there anyone with any questions? Or who would like to go first?
This is really, I forgot to insert this in here. I wanted to point this out. Again, from the point of view of the commercial VCSEL world, there was this transition in 2017 going to all arrays. And these were sort of the application space. Before that, Datacom kind of ruled. This has always been kind of out there. But it's since 2017, it is all about arrays. It's all about consumer products. And in fact, when I say that, it's even affected the wavelength. That before this, 850 nanometer was sort of the convention because that was the easiest and most, well, actually I say 850 nanometers, but we were using in-gas quantum walls to be reliable. But this was considered to be the standard. And because of the fact that at 920 nanometers outside, you have the least amount of solar background, 920, simply because of these sensor applications became now the dominant. And so basically, when you're looking for, if you go out and look for VCSEL wafers, you just find 920 nanometers as being the sort of the standard. So again, and this is all being driven by by this consumer products, and realized, and there was some really serious conversation when we were looking at making billions of pixels. Was there enough gallium in the crust to support this? And by the way, this is now a political thing, in that China is no longer allowed to sell the United States gallium arsenide substrates. Again, this is striking right at the, there's a lot of manufacturing of 3.5 pixels in the United States. So, so in some sense, again, there's other ramifications when things become a commodity, that it becomes almost political aspect. Anyway, I just thought I'd point that out.